Parametric design can feel like a catch-22. If you know what you're trying to make, it can be really easy to make a script. But on the other hand, sometimes you can miss out on those nice design mistakes that arise during the process. I find the way to manage this is to make sure that you understand the parameters that you're using and have a good knowledge of how to play with them. So today we're going to explore this by recreating the MAHA NAKON by Scheeren and then playing around with the parameters. Let's see what we come up with. We're going to start with a rectangle component as the base of our tower. We'll create a slider of 100 and make that the base size. So this is going to be plugged into the X and Y inputs. I also want a bit of control over where we place this tower, so we'll create a point in Rhino, point in Grasshopper, right click, set one point, select the point in Rhino, connect the point to our plane in Grasshopper, and then middle mouse wheel and select the blindfold icon to hide that point. Can then move the point around in Rhino until we're happy with the position. Next, we'll pull out a divide domain squared component, not the standard divide domain. We need to make sure that the little squared is there as well. This is critical for working with surfaces. We'll then convert the curve of the rectangle to a surface and then surface through to domain. Now next I'm going to divide the 100 base size by the ideal cell size. So we'll make our cell size 20. This will effectively result in a division of 5. We're going to copy this division across, click and drag, tap Alt, and it will create a copy for you. Connect that through to the V count. Next, we'll divide the surface with an isotrim component. So connect your surface through, and then the segments is our domain, and you can see that the original surface has been split. Now, instead of hitting this blindfold icon, you can select the components that you want to hide and hit Control Q. It's a shortcut for hiding things. Very, very useful. Also, just type in hide to hide that Rhino point. Okay, so next, let's make these into 3D cubes instead of squares. So we'll extrude those base surfaces in the Z direction. Next, we'll give this a factor. Now, to make these cubes, we'll just take that same ideal cell size of 20. We'll plug that through, and we've got our grid of cubes. Finally, to make it into a tower, we'll move all of those cubes again in the Z direction. And we'll move that in a series. So connect that through. And we want to, first of all, define how many levels we'll have. So we'll start off with 40. That will be our number of levels. We also need to define the step size. So in this case, it is 20, which is the height of our cubes. If we plug the number of levels into the count, I might just drop that down to 20, we can see that something isn't quite right. Now we'll do another video on the effect of grafting, but for now let's just graft the geometry component of move. We can see that we've got our tower here. So we'll hide the extrude with that Control Q command. And just as one of the final steps, we'll add a volume component. This will give us the center points of each of those cubes. And then just to prepare for the next stage, we'll select everything and hide it. Let's start by unhiding our original base square, and we'll pull out a divide curve component. We plug our rectangle through. This will divide our curve into a series of points. Now we don't need too many for this exercise, but these points are going to be what's defining our reduction line. Next, we need to move those points once again in the Z direction. We're going to take the number of levels and times it by the height of our cubes. So we'll multiply those numbers together, connect through the number of levels and the cube height or cell size, and we'll also need a range component. So connect that multiplication through as our domain and the number of points as our steps. When we connect that through, you can see that each of the points are moved up incrementally. And we can connect them with an interpolated line. This will give us the smooth wrapping line that we're looking for in recreating the tower. Let's turn on our tower and points again and pull out a curve closest point component. We're going to put the centroids in as our points and flatten the output of the tower geometry. We'll input the interpolated curve as our curve and then sort for larger than 20. This will be our first number to test against, and it will give us an output of true and false values. We can use that to inform a cull pattern. So connect the larger than as our list. We'll hide these away, also these, and connect the output geometry of the tower to our cull pattern list. We can sort of see what's going on now, but it's a little bit hard to actually view. So let's just hide everything for a moment. We'll add a custom preview and a swatch. So we can double click to change the hue. And we can drag around to find the color we want with various sliders. Plug that in as our material. We'll also change to a rendered hue. Hide the original rectangle and plug the cull pattern list into the geometry. Here we can see the basis for the tower. So the goal wasn't simply to recreate the tower, we also want control over it. So the first simple alteration you can make is to change the distance at which the cubes are reduced. So if we plug in a slider to the larger than component and increase it from the base 20, we can increase the distance at which cubes are reduced. So here we see a far greater reduction. Pulling it back down under the original 20, we can see a far lesser reduction. Another simple alteration you may want to make involves the points of this divide curve component. To alter the slope of the reduction, simply right-click the point output and select reverse. You may also want to control the starting point of the twist. Let's drop on a seam component, right-click and reparameterize the curve and add a slider from 1 to 0. If we imagine the original square as a line connecting its endpoint and its start point, this slider from 1 to 0 represents where along that line the seam actually is. We then replace this curve and play with the slider. It gives us control of where that line is actually being produced. If I unhide the interpolation line and the moved points, it's a little bit easier to visualize. Another simple change that we can make is to change the type of line. So we'll change to a polyline. Hold Control and Shift to rewire from one component to another. We'll pull the vertices across and the curve output. We can see that we've got more of a straight-edged line. We then change the number of points as the input. You can see that there's a different effect. So now we're going through at some points of the tower rather than all the way around. Changing that further gets a more direct line through the tower. It's a quick way to get a big change. Let's take one more look at how we can change the point order to get a difference on this tower. So I'm going to set up another interpolation line and a point list and drop this down to 4. The points are ordered from 0 at the bottom going through to 4 at the top. If we add a jitter component and connect that through to our demonstration components, we can see that the ordering is no longer from bottom to top. It's been changed. Adding a slider into the seed changes the random value. at which the list is jittered. If we bring that up to 6, we'll be able to get a nice messy line. I'll delete these demonstration components, hide away those points again, and connect through the jittered list to our interpolation line. We can see the effect that has. As I move this slider around, we can see that we've got many iterations available. To finish off the tower, we'll mostly work in this area. So I'll start by locking the canvas. This means that nothing will compute while I'm altering some data here. So the first component we'll get is duplicate data. We use this to duplicate the points that we've created in the divide curve component. We'll also get a multiplication unit. For now we'll use the slider value 2. We'll connect that number to duplicate data, disconnect the domain from our range, and replace the steps as the input for our multiplication, and finish tying that into our steps. We'll also pull out a graph mapper. I'll show you what this does in just a moment. For now, let's change it to a Bezier curve. And we'll also need to remap those numbers. So for now, we'll put it in the value. Now I'll unlog to show you what some of these changes have done. First of all, the domain is now from 0 to 1. Our multiplication is still that cell size times the number of levels. The value of our range is now going from 0 to 1. And a target is currently 0 to 1, so let's change that to our target of 800. This will remap the numbers from 0 to 1 to 0 to 800. So when we plug that through and reload, we can now see that the line is wrapping around the tower twice instead of once. So to make the final changes to replicate the tower, we're going to change the seam back to 0.5 and also just slightly increase the reduction distance. Finally, we'll alter the Bezier curve, which redistributes the way that the twist goes up the tower. Quick cleanup, and then finally, just to show you the effect of this in more detail, we can wrap it 3, 4, or more times around the tower and get a tighter twist. We'll pull the value back to 2 to finish off the tower. So that's it for today. If you followed along, feel free to share your result in the comments below. Thanks for watching.